Lesson 4 is about passive mode locking, the second category of post-generation techniques. And I divide this lesson into 4 sections, starting with derivation of the master equation, the governing differential equation that allows us to calculate the steady-state pulse in a passive mode lock laser. Then it's passive mode locking with self-amplitude modulation only. Self-amplitude modulation. So it's an effort to get solution to the master equation, but under a relatively simple situation where only amplitude modulation is taken into account. After that, we can generalize the solution to the case when both amplitude and phase modulations are taken into account. So you can see the effects of self-phase modulation and the group velocity dispersion, which we have seen in lesson 3. And by the end of this lesson, I would like to introduce sort of the details of current length mode locked disulfide lasers, which for many decades the most important driving lasers in the femtosecond regime. Okay. So there are 4 sections. Starting with some basic ideas. What are the disadvantages of active mode locking? We have seen active mode locking in lesson 2. But what are the problems of those lasers? I summarize into 2 points. The first one is the modulation frequency must precisely match the cavity mode spacing. In other words, FM means modulation frequency of the external modulator equals delta F. Delta F is the mode spacing. If you still remember in the midterm exam, you are asked why in steady state a cavity can only permit discrete frequencies. And the spacing between 2 adjacent permitted frequencies is the delta F, okay? So they have to be the same. Or in time domain, it means Tm equals Tr. What is Tm? The period of the blue curve. Blue curve is the transmission function due to your intensity modulator. The Tr is the repetition period, pulse to pulse spacing to your laser cavity. These 2 numbers have to be the same. That means synchronization is necessary. Okay? However, this is usually a tedious task because they are 2 independent parameters, right? If you drive your modulator with the modulation frequency, you rely on an electronic driver. But the pulse trend is up to the laser cavity. Tm is your X. There are 2 independent parameters. So if you don't do anything, they should be different. Okay, at least slightly different. Then you have to spend a lot of effort to lock them together, usually a feedback loop. Okay? If they are not synchronized, can you imagine what would be the problems? 这个图画得很完美，它们是同步的。那如果不同步有什么问题？ If the transmission peak is misaligned from the pulse peak, what would be the problem? your post-shortening effect would be disturbed. Okay? At that time, maybe the post cannot be shortened, but broadened if the misalignment is really serious. But other than that, there is timing issue. Okay? So you can imagine if the post peak is slightly to the right of the blue peak, then what happens after the post passes through the cavity once? 你想一下啊，现在是对齐，很完美。那如果这个红色的 peak 大概在这里，也就是相对于蓝色的 peak， 它慢了一点，才出现这个 post peak。下一个跑了一个 round trip 之后 ，what happens? Peak will be attenuated. The left shoulder relatively stronger, so your pose has some distortion, but there is timing issue. So simple question is, after one round trip, will be the misalignment even serious or becomes less serious? More serious? Any other opinion?
靠左边的那一部分会爆，然后它原本尖的地方掉下来，然后 pose 可能会小一点。可是如果你一开始misalignment很严重。
Yeah, distortion is for sure. But here I'm asking the timing issue. 时机，我就不管它变形啊，我只是说跑了一个 round trip 之后，你本来假设有一单位的 misalignment， 靠右的 misalignment， 跑了一个 round trip， 你会维持一单位的 misalignment， 还是变小的 misalignment， 还是变更严重的 misalignment？ 有 three possibilities. It's science, it's not democracy, so we cannot determine it by voting, right? Could you justify if you have some idea? 有没有人想要试试看？ Remember, I just mentioned, after one round trip, your post peak is smaller, but your left shoulder is higher, while right shoulder is even weaker, right? So what would be the change of the timing? It becomes less serious, the error becomes smaller, right? 简单说，重心左移了嘛，因为你的变形导致重心左移。你本来是偏右的，重心左移就是这件问题变小了。So there is a self-healing mechanism in this picture. Okay, so but it's another story. I just share some insight about the synchronization issue. Okay, it's not just about post-shortening. It's also about the timing. Okay. The second problem is the post-shortening effect becomes ineffective for very short poses. I've seen that because post-shortening is up to the curvature of the blue curve. When your optical pose becomes shorter and shorter, it will see a relatively flat modulation curve. And a flat curve does not shorten the pose anymore. Okay? And the blue curve is a fixed curve due to your external modulation. It does not change. Okay? So sooner or later, it becomes ineffective. That's why you cannot generate femtosecond poses by typical modulator, active Molag lasers. Okay. So these are the two disadvantages, major disadvantages of active Molag lasers. Is passive Molag-ing, PML, passive Molag-ing. The idea is quite easy. We just place a saturable absorber inside the cavity, which is shown here, the blue one. Okay? and it can provide intensity-dependent loss. Your loss coefficient L is not a constant. It's a function of light intensity, I. Okay? So the picture is like this. You have cavity, you have gap medium, but they are required by any lasers, even CW lasers. The only difference is now you place a saturable absorber here, very like the external modulator in active Molag lasers. The difference is now you do not need external driving source. Okay? But any modulator relies on driving source. Where is the driving source now? The driving source is the optical pulse itself inside your laser cavity. Okay, so your optical pulse serves as the driving source to your modulator. So your modulation function will change with your optical pulse. It's no longer a static modulation curve. It's a dynamic curve. That's the fundamental difference from active Molag. Okay. And the modulator is so-called saturable absorber we introduced in lesson 3. Any question? So we replace external modulator by a saturable absorber. What would be the advantages? Fortunately, the replacement can solve the two difficulties encountered in active Molag. Okay. Number one, the pulse itself drives the loss. Okay. So automatic synchronization. In active Molag lasers, you need a feedback loop usually to force the modulation frequency equal to your mode spacing. It's uneasy. Takes time, takes effort, takes cost. But here, nothing, because it drives the modulator, so it's automatic. Without any extra effort. The second advantage, sort of a loop. Okay, say you have a shorter pulse, it will induce higher intensity, just like the second picture. Okay, the left one is weaker pulse, but when the pulse width is compressed, you got higher peak intensity, shorter pulse duration, if we assume the energy is the same. Okay, so you have higher intensity, then it will induce greater nonlinearity, such as single phase modulation. Okay, the higher the intensity, the stronger the nonlinearity. And if the pulse shortening effect comes from the nonlinearity, that's for sure, as we will see, then that means you have stronger pulse shortening effect. Then you can go back to the initial point. You got even shorter pulse. You got even higher intensity. You got even greater nonlinearity. Then you got even stronger pulse shortening effect. So you have a positive feedback loop. The effect intensifies itself from round trip to another round trip. Okay. Then it's highly possible you can generate extremely short femtosecond pulses. Okay. So the blue curve means the modulation curve. In active Molag, the blue curve is static, does not change with the pulse evolution. But in passive Molag, as shown in these two figures, when the pulse is weaker or broader, the modulation curve is shallower. But when you got stronger, shorter pulses, the modulation depth increases accordingly. Okay. 好，所以这是一个非常聪明的设计啊。随着你的脉冲逐渐在压缩，你的调变能力其实也跟着加强。那它就有办法让一个已经很窄的脉冲变得更窄，一直延续这个压缩下去。OK， 所以你可以产生极短的脉冲。 Now the question is, why can't we get delta function, 0 pulse width, if the positive loop looks so great? What would be the limiting factor? One possibility is crystal damage, but usually our passive Moloch laser give you maybe femtosecond pulses without crystal damage. So before the damage, something happens. Then the positive feedback loop stops. Which one? The blue curve? Why? But as I mentioned, the blue curve will change with the red curve. So it can be higher and higher curvature. Okay, that's one possibility. This evolution is under the assumption we have fast sexual absorber. If you have slow sexual absorber, the curve could not be so ideal. But as you will see in section 4-4, in Thai sulfide lasers, we use current Moloching. It's always fast sexual absorber. Yes.
保护吸收体的 loss 掉到0，然后再往下掉。
掉到0。
所以它的 gain 跟它光区分。
Oh, okay, I know what you are talking. But even the highest peak intensity, maybe, but it not happen very usually. It's so high such that your 100% transmission, 0 loss. That's what you mean, right? But remember, you always have power 0, your tail, post tail 0. So the transmission must be lower. So there is always a modulation depth. 是不是？你的时候一定会有0，就是没有 power 到某个 peak power。你 peak power 可能很高，高到 transmission 是100%，但你这里一定在啊，一定在它的 transmission 就不会是100%，那个 difference 一定还会在。Modulation depth will never vanish. SP, the stronger the better. Broader bandwidth. That's not bad for short pulse generation. Why? If we have fast sexual absorber, 为什么这个 curve 会 settle？ 说就不再有这些凹下来。
它没办法再继续变得更深。
If we assume we have fast sexual absorber, which is possible in current Moloching, the blue curve is always there. Okay. The fundamental limit should be the gain bandwidth. It's material-wise, right? Even this picture is so great. Whenever you broaden your spectrum to the as wide as your gain spectrum, that's the end. Because outside the gain bandwidth, you cannot amplify the light. So you can hardly broaden the spectrum even stronger. Okay. But there is some exception, I have to admit. But fundamentally, that's the physical limit. So you cannot have delta function.